Hello everyone, in this video we are going to explore the volume grid nodes that are recently added to Blender 5 and they are really versatile. Now it is possible to do really amazing things with these nodes in Blender. For example, we can create the custom forces for the particles, we can do custom fluid simulations, we can edit or modify the VDB data, and we can also do the SDF modeling with these nodes. So in this video we are going to use these volume grid nodes to do the curl noise effect. Because of these nodes we can visualize this noise for really large number of lines or particles. So let's get started. So first I'll go through these nodes and the grid concept, and then we're going to build the curl noise for the lines as well as for the particles. This is the blog post about the volume grid nodes. I highly recommend you please read this. Okay, let's add a plane. Let me add the geometry nodes and also let me delete this. Okay. So let's start with the existing volume nodes, so that will help you to understand the new concept. If I add the mesh volume node, we have this, then we have this point to volume. So we have these nodes. So with these nodes we can generate the volume from a mesh. If I connect this and add a cube, see, we are generating the volume from this cube mesh. Similarly, we can do that from the points. And if I duplicate this and add a cone here, so now we can generate the volume from a cone geometry or cone mesh. So if we combine them, we can't see anything. So basically it is difficult to combine these volumes. So after these, then there was added the volume cube node. So with this node, we can combine the volumes indirectly by combining the densities, because in this case the density is field and in this case the density is a single value. We can't input a field to this. Okay. However, if we plug that into this, and we can generate the volume based on the noise field. See, we can also generate the volume by combining the density from these meshes. Like if I add the mesh face fall off node, make this 0, duplicate that, and then combine that and plug that into this. So basically we are generating the density based on this distance function, and now we have this volume. So indirectly we are basically combining the volume from these meshes. Okay. So if we want to combine or edit or modify the volume, we need to separate the data from the volume. Okay. So let me delete everything. We need this. So we have this volume. To get the data from this volume, if we add the named grid node, so that provides the volume, so this volume, and also provide the grid. And let me disable this option. So here we need to specify the grid that is carried by this volume. In this case it has density. So now we can have this density grid. So we can directly view that in the viewport. See, we can also view the volume, and we can also view this grid data directly in the viewport. And you may notice that this is no longer limited to float. You can define integer, boolean, or vector grid. Okay. The next question is, what is grid? Because if we want to separate the data from the volume, we need to store in some format. So for that, the new concept, the new data format is the volume grid, that is made up from the voxels and the data stored on these voxels in terms of tiles. Okay, so let's go step by step. So let me first add cube. So in case of geometry, we can store the attributes. Let me add that here. Okay, so we have this. And if we want to store something, let's say we want to store some random value, then we need to specify the name, let's say X, and then we need to specify the domain, so where this data is living. Okay, or you can say the location of the data onto this geometry. So we are storing this information onto this geometry at points of this cube. Okay, so in this case the volume data is stored in grid, so that is 3-dimensional grid, and the building block of this grid is the voxel. Like in this case we have this point is the main building block of the geometry. If we connect them, we have edges, and if we further connect those edges, we have the faces. Okay, in this case we are not directly storing the data onto the voxels. we are storing the data in terms of tiles onto those voxels. If we directly store the data onto the voxel, so that is really inefficient and really expensive for the computations. So the data is stored in terms of tiles, and one tile can be made up of a bunch of voxels. For example, it can be 8 by 8 by 8 voxels. Okay, I further explain this concept when we store a new grid to this. Okay, and then we have this grid info node. So this node provides the information about the transform as well as the background value of the grid, and here you can specify the type of the grid. Okay, next we have the voxel index, so that is similar to this index node. Okay, so in this case it provides the indices of the voxels for the grid, and it also provides the information about the tiles. So for this volume, this grid has 32 resolution for all the axes. It means we have really large number of voxels for this grid, and let me visualize that. Basically, you can think that this each point is representing a voxel of this grid. If we go to the front mode, and this voxel, this one is 0, 0, 0, because it is three-dimensional grid, so we need 3 integer to specify the voxel. This node provides the indices for all the voxels as well as for the tiles. Okay, we have these nodes to sample the data from the geometry, and similar to that we have these sample nodes to sample the data from the grid. So we can use this node to sample the grid based on the position. Okay, or we can use the sample grid index node to sample the grid based on the voxel index. Okay, and after that you can advect the grid, you can calculate the its curl, divergence, gradient and Laplacian, and then you can also write new grids. You can set their backgrounds and you can also set their transform. So let me add that. So similar to store named attribute node, we have store named grid. So with this node we can write a new grid to this volume. By the way, you can write any number of grids to a volume. Okay, so to write the grid we need to specify its topology. We can borrow this topology from the existing grid, like in this case the density. So you can like multiply that with 0 because we don't want any data from this grid. Okay, see it is 0. So this is before, this is after, and let's say we want this to be a vector. So we can either add a vector node and then plug that into this. So here we can input whatever data we want to write onto this grid, and here you need to specify its name. And let's say we want to write a noise texture or noise data to this. Let me change that to vector. Okay, see we have this vector data, and now you can see these tiles because we are getting the topology from the density, and that density grid is tiled. Okay, so we need to untile that, or you can say we need to break those tiles into voxels. So for that we have a dedicated node, that is this voxelized grid, that basically removes the sparseness from a voxel grid by making the active tiles into voxels. Okay, so if we add that, see we have this nice noise data. Let me decrease the scale. See, this is really smooth. So this is before and this is after. So now you may ask, okay, how to tile that back? So for that we can use the prone grid node. So here you need to select the type of the grid. Then you have different modes like inactive mode, threshold and STF. And with this threshold, basically if you specify the threshold value, you can convert those voxel back into tiles. Okay, suppose in the grid we have some voxels that have same value. So let's say some bunch of voxels, let's say 2 by 2 by 2 has some value, let's say 0.1, and instead of storing that 8 voxel we can store only one tile. So that is the beauty of this. So basically we can make that grid more efficient with this node. Okay, for the color noise we need the voxelized grid or the data at the voxel scale. There is another method to store this data, so that is the field to grid node. here you need to specify the topology, so that we are getting from this density grid, and then you need to plug the field, whatever field you want to store. So here we want to store this noise vector field, so to generate this vector grid, and we can plug that into this. Okay, so that is really clean way to store the field onto the grid. Okay, so after that you can do different kind of operations, like when you can calculate its curl, divergence, Laplacians, and gradient. So now we have this new grid, and we can calculate it is curl. So grid curl. Okay, so this is the noise. Now we have this curl of the noise. Next we need to sample this information from the grid. So we can use the sample grid node. We can sample the skull based on the position, and here we can specify the interpolation method. Okay, and let me distribute some points in this volume. Now see, we have this information about the curl noise onto these points. Now we have this information of curl noise for the points. Now we can basically play with this and generate really nice visualization based on this noise. Now let's first visualize this noise with the lines, and then we're going to visualize that using the particles by using this noise as a custom force. Okay, to trace that noise with the lines, we need to build the tracer. So that is really easy. First, let's add the icosphere, and then we're going to distribute some points onto that, and we have these points. Then we need to store two attributes to build this tracer. So let me add this node, duplicate that. So first we're going to store the integer. So that is going to be the p index, the index of the original points. And here we need to store the mask. So let's call this p active, so that we can identify the active points. If you want to learn more about this tracer, you can watch this video visualizing the electric field with the geometry nodes. In that I have provided the detailed information. Okay, so we have this, and then we're going to add the repeat zone node and plug that into this. So in this zone, first we're going to add the separate geometry node, and we're going to separate the active points. Let me copy that here. And also we're going to deactivate these points. Okay, and then we're going to add the set position node, so that we can offset these active points. And after that we're going to combine these points with these points. Okay, so now we have this tracer. Let me add 0.1. If I increase the iteration, see, we have these lines made from points. You can easily convert these points into curves using the point to curve node. But see, it has connected all the points. So we need to specify the ID. We don't want to connect all the points. We want to connect each point that has specific this p index. Okay, so let me add the named attribute node and specify the p index. See, and you can see that here. Let me decrease the number of points and also enable this thing. See, the points that has unique p index are connected together. So we have these curves. Okay, nice. So now we're going to offset these points based on this curl noise. Okay, so first we're going to normalize this, so that we don't have any effect of the magnitude onto the offset. And then we're going to add the v-scale node, so that we can control the offset. Okay, maybe 0.1 and 0.05. Okay, maybe 100. I think 0.025 is fine. And then we can increase the density of the points. Maybe 150. See, now we can visualize this skull noise with the lines. See, it's really fast. You can even change the noise. Only thing is that it is confined to the size of this grid. Okay, and after that you can convert that into a mesh. See to mesh node, and here you can add the file, maybe circle, maybe 3.001. Okay, and then you can add the material and render that. Okay, so next we're going to visualize this color noise using the particles. Okay, so for that I'm going to use the particles from the extra nodes. Okay, so let me first add the cube, and then we're going to add the case distribute node. So we have these points. So in this case we're going to increase the xy scale and decrease it is z scale, something like that. Then we're going to increase the surface density as well as the volume density. Okay, then we're going to add the xpvd solver. Okay, and after that we're going to add the xpvd instancer, and here we're going to instance the cube. Okay, let me move that this side, and in this case we're going to use the custom scale. So make this 10 and decrease this to maybe 0.02. Okay, go to the simulation, decrease the substeps because there is no self collisions detections, so we can use 2. And in the emission we can decrease the end frame. Basically we want all the particles should be emitted within this range. Okay, and after that in the dynamics we need to input this as force. Okay, so for that we have this field force node, so we connect that to the field and then connect that to the force. And in this case we don't need any velocity from the previous frame for the particles, otherwise particle will gain the velocity with time and then fly off. And also we don't need any drag. Okay, so let me increase the strength. Okay, the motion is fast, so we can also slow down that using this time step. Basically we can decrease the time step by half, so now it is slow. And another thing we can do is that we can play with this scale. So let me first add the xpvd info node, so that will provide all the attributes of the this particles. And here we need the velocity of the particle, and then basically we can affect the size of these particles based on their velocity. Then add the xyz node, and I mainly want to affect the x-axis scale of these particles. Plug that into this, so this should be maybe 0.05 and here maybe 0.01. Okay, here we can tweak this, maybe something like that. See, and this node also come with this material, so we can use that. And let me add that here. So you can let me also make this local, so you can use these attributes of the particles to add the material. Like we can use random, or we can use this age base factor. See, initially all these particles are blue and then they slowly transition to white. Or you can use different, like you can use the velocity to visualize. I think I used velocity in the final render. And here you can input any object, like maybe we can input a cone. So we have these cones. Maybe we can increase its depth, maybe 5. So now we are visualizing this noise with these cones. So there are a lot of possibility and you can create really amazing visuals with this. So this is how you can easily create the curl noise using the volume nodes, and you can use that as a custom force for the particles, or you can visualize the noise using the lines. This is it. You can get the project file from my Patreon page. I hope you learned something from this videos. If you like, then please like the video and subscribe to my channel for more updates. So thank you for watching. See you in the next video. Happy noding. Bye.